So this relationship that we saw in the last example between a linear system of equations and its associated homogeneous system, that relationship doesn't hold for just that one example. It turns out that it is a general rule for all linear systems. We summarize the results here in this theorem. Okay? Suppose x sub p is a particular solution of the linear system ax equals b. Okay, so what does that mean? It means that if I plug this in for x, it makes the equation true. Okay, it means that a times x sub p does actually equal vector b. Okay, that's what it means to be a solution. You plug it in, the equation's true. Now, we are just a particular solution. We've seen with linear systems of equations that we could have no solution, we could have infinitely many solutions, we could have a unique solution. In this case, we're saying we do have at least one solution, okay? So we know the system is consistent. We know we have at least one solution. But we don't know if we have one solution or infinitely many solutions. And in fact, it doesn't matter. Pick one of the solutions. If you have only one solution, pick that one. If you have infinitely many solutions, pick one of the solutions from the infinitely many number of solutions that are available. Just pick one particular solution. Does not matter which one. Okay, that's what x sub p is. And we have two results. Result one, if x sub h is a solution to the associated homogeneous system, then if we add our particular solution with our homogeneous solution, that sum is a solution of the original linear system also. Let me write what that means in symbols. If so x sub p is a particular solution, so when I plug that in, I solve the equation, I make the equation true. So this actually equals this. Ax sub p actually equals b. And for part A, we are assuming that x sub h is a solution to the associated homogeneous system. So that means if I take my coefficient matrix A and multiply it by our homogeneous solution x sub h, we will get vector 0. Okay, this equation is also true. So we're assuming these two facts hold. Then the conclusion is that the sum of those two solutions is also a solution to the original non-homogeneous system of equations. So if we take their sum, x sub p plus x sub h, and we plug it in for x in the non-homogeneous equation, then the equation will be true. It is a solution to this non-homogeneous equation. It is a different solution. Okay, I should say potentially different. We know that for a homogeneous solution, we always have the trivial solution of the system, the vector of all zeros. Sometimes we may have non-trivial solutions. What this is saying is that if you take a solution to the homogeneous system, whether it's trivial or not, and add it to a solution that already exists for the system, then that sum will also be a solution to the original non-homogeneous system. Okay? Now let's look at part B. If x1 is a solution to ax equals b, so x1 is a solution to the original non-homogeneous system, just like xp. xp is a particular solution. x1 is a different particular solution. Again, I say different, I should say potentially different. It could be the same. The result will still hold. Okay. So if we take a potentially different solution of the non-homogeneous system of equations, then there exists a solution of the associated homogeneous system, x sub h, such that I could describe this new particular solution as a sum of my old particular solution plus some solution to the associated homogeneous system. Okay? Okay, I'm going to leave part A for you to prove on your own. But part B we're going to prove together. So this part B is saying there exists an xh such that this holds. So if we can find a vector xh so that this is true, we will have proved the statement. We will have proved the theorem. Okay, so that's going to be our goal. Can we construct xh and prove that it satisfies these criteria? Okay, so I know x1 equals xp plus xh, so I could choose xh to be, say, x1 minus xp. Okay, if this theorem's true, then this is what xh should be, right? Just doing a little bit of algebra here. Okay. So set vector xh to be the difference of my two particular solutions. My particular solution x1 and my original particular solution xp. Both of these are solutions to the non-homogeneous linear system. Now I need to show that xh is a solution to the associated homogeneous system. I know it's a vector, right? I definitely can subtract these two vectors. I'm assuming I have these two things to begin with. That's part of the assumption. Okay? And when I have two vectors, I can subtract them. So x sub h exists. What I need to show is that it's a solution to the associated homogeneous system. If I could show that, I'm done. Okay? Then what I need to do, if it's going to be a solution to the associated homogeneous system, that means my coefficient matrix A times my my potential homogeneous solution x sub h. If this is actually a solution to the homogeneous solution, to the homogeneous system, I better get vector 0, right? So I need to show that that's what I get. Now to do that, I'm going to do a little substitution here. I've defined my vector x sub h to be the difference of x1 and xp. So let's plug in what I've defined x sub h to be. So instead of x sub h, I'm going to substitute in x1 minus xp. Okay. Now let's do a little distribution with matrix multiplication. So I get A x1 minus A xp. And now we're almost done because x1 is a solution of the original non-homogeneous system. So that means that if I plug in x1, I better get b out, right? So a times x1 equals b. And that's exactly what I have here. I have a times x1, so I know that equals vector b. And similarly for x sub p is a particular solution of the non-homogeneous system, which means if I plug it in for x, then it makes the equation true. So a times x sub p is equal to vector b. And that's exactly what I have here. I have matrix A times vector x sub p. So that also equals vector b. And I'm subtracting them. So I get vector b minus vector b. When I take a vector and subtract itself, I get 0. And so I've shown what I want to show. The coefficient matrix A times vector x sub h is equal to 0, which means, by definition, this vector x sub h, which I have defined, must be a solution to the homogeneous system. Thus, x sub h is a solution to the homogeneous system. And because of how I defined it, x sub h equals x1 minus xp, if I just do a little algebra, I get the result I want, meaning vector x sub p, I'm sorry, x sub 1. Vector x sub 1, our new particular solution, just our old particular solution plus a solution to the homogeneous system. That was the claim, that I could find an x sub h to the homogeneous system, so this was true. Okay? I picked x sub h, I showed it was a solution to the homogeneous system, and because of how I defined x sub h, this equation is clearly true. So I just want to kind of summarize what this theorem says, because it's an important idea here. It's a relationship between all linear systems with the same coefficient matrix. Okay? It's saying that they're kind of parallel solutions. The only thing that changes is the particular solution. The only thing that changes is kind of the position of the solution. Okay? Once you have a particular solution, your solution to the homogeneous system kind of tells you where all the other solutions live. To get to any other solution in the system, you just take your particular solution, then add some solution to the homogeneous system. Okay? And so you will have these parallel solutions. The only thing that changes is their position, the particular solution x sub p, but their shape and their structure are going to be determined by the original homogeneous solution.